But this we wanted to do in a very specific context, and this was a recent discovery from Loadgap, who works in the lab of the Mosers, the Mosers, who are of course at the beginning of this whole discussion on grid cells and their importance in the representation of space and spatial cognition. And Loadgap and his co-workers published a really interesting paper where they morphed the environment. Okay, so what they do here, so here we have an environment, let's say it's rectangular, okay, and we morph this environment in steps of 10 minutes from a rectangular environment to a circular environment. And on the next day we can do the reverse. Okay, so now if we measure in CA3 or the dentate gyrus, then here we have the representation, the responses of this neuron overlaid on the trajectories of the animal in this space. And if we go now look at this representation here, where we go from rectangular to circular, or from circular to rectangular, in CA3 we still see fairly specific responses to space, right? That don't seem to be affected a lot by the morphing itself, while in the dentate gyrus we would see more variability, that we see neurons that can give us a response in the rectangular environment and can give us a response to a different location in the circular environment. And so that means there's a dissociation there between CA3 and the dentate in the response to the properties of the environment. Remember, the only thing we're changing here is really what the environment looks like. When I move through this environment, so with respect to my grid cells, the responses should stay identical. Okay? So what they subsequently did, they calculated a population vector where essentially they took all the neurons they were measuring from in CA3 or the dentate, and they just looked at the correlation of this population response as the environment was morphed. And now we see a somewhat different profile between CA3 and CA1, CA3 and the dentate. So in CA3 we see a rather smooth decline, but in the dentate we already see a lower population vector at the first step. So the impact of this correlation, the similarity between the population response as we morph the environment, is much stronger for dentate as it is for CA3. And that then raises this interesting question of how we can account for this so-called rate remapping. Right? Because if now the environment is morphing, I'm sort of remapping my response to the environment I am in. And the hypothesis that we pursued is, let me see if I have a, okay. The hypothesis that we pursued is that this, so the medial entorhinal cortex, which gives me the grid cell response, we assume is not changing. If I move in this environment, let's say in this rectangular area here, my displacement in XY will stay the same, even though whether this building, the rest of the building is here or not. Right, so my grid cell responses should be the same. However, all other sensory information I receive should change. So our hypothesis was that this rate remapping we observe is the result of changes in the inputs I receive from the lateral entorhinal cortex. So essentially what we did is we took a fairly anatomically detailed model of the dentate gyrus, and we looked at how the projections from the medial entorhinal cortex and lateral entorhinal cortex would now account for the rate remapping that was reported in the literature. So here you see an example of the responses of my grid cells in a circular or a rectangular environment for simulated cells of our medial entorhinal cortex. Here we see as for a comparison firing rate maps for recorded neurons. Here the same thing for the lateral entorhinal cortex, where, as we discussed earlier, we have higher variability in the responses to sensory stimuli. Then we look at our integration. So here now we have our rate remapping result for the dentate in the real animal and here in our simulation, and we see a similar kind of variability, where we also see a similar kind of decay of this population vector correlation that we were seeking. Of course, we didn't stick just to this more phenomenological description, not just like, oh, this picture looks like that picture and therefore it's a good model. We have quantified this. So we really looked at, let's say, different, the stages of morphing. This is the decrease of the correlation vector you would get in the case of load gap, what they reported. Here is the change in the population vector we get in our model with varying the gain parameter that controls the mixing of the medial and lateral entorhinal cortex. So what we show is that with a gain of about 0.4, we can essentially account for the population vector results reported by load gap, which means, in conclusion, that for us, we say, well, the rate remapping load gap observes is the result of the changes in the responses to the lateral entorhinal cortex, while those to the medial entorhinal cortex remain constant, and we predict that the contribution of the lateral entorhinal cortex to this response is about 0.4 as compared to the contribution of the medial entorhinal cortex. So our prediction in the dentate gyrus, the medial entorhinal cortex sets, let's say, a context for firing. It roughly determines which cells are eligible, if you want, to fire, but the subset of cells that will actually respond will be those that gets the highest drive from the lateral entorhinal cortex. And this then expresses this competitive inhibition rule that John Lissman also has proposed in his earlier paper. So it means we can account for rate remapping in very quantitative terms by a model that is well constrained by the biology, but also making a prediction that is directly testable. And that is a prediction on how the synapses originating, or the ratio of synapses originating in the lateral entorhinal cortex versus those originating in the medial entorhinal cortex, and that this ratio should be bound to 0.4. So maybe as a last aspect to just highlight, even though it's not really described in the results here, the rate remapping that has been observed in the dentate gyrus shows a very interesting dependence on the position. So dependent on the position of the animal, you might see different shifts in the responses of the neuron as in other positions. So that means this rate remapping seems to be sort of modulated by the position the animal is in. As if, dependent on the position, the neuron in the dentate gyrus is conveying a different set of responses from the lateral entorhinal cortex. So how we are interpreting this now, which we are very excited about, is that this might be indicative of some sort of multiplexing of this information. That dependent on your position in space, you allow a certain subset of inputs from the lateral entorhinal cortex to be transduced to CA3 versus when you are in another position in space. In some sense, you could interpret this as a sort of a space-dependent attentional modulation, to use this more sort of high-level interpretation. So we're very pleased with these results, and they will appear in Neuron in December. So thank you very much.